In lab, you guys looked at three relationships. First, you took and you measured pressure and volume and how those two were related when temperature was held constant. So you used a syringe to trap a constant amount of gas. So there was actually two constants in here. You had this syringe that was sealed. So once you had your system set, this was hooked up to our pressure sensor, so there was no other gas that was going to get into this, and then you had your plunger right. And so this was a sealed system. There's gas particles in here, and there's a fixed number. Okay, so the amount never changed, and then you were able to vary the volume back and forth, but the temperature never changed. So the number of particles and the temperature were fixed in this. And hopefully what you saw was that as you decreased the volume, the pressure increased. So these have an inverse relationship to each other. So volume was here because it's your manipulated variable, and pressure was over here. This is what you measured in response to that variable, and you should have seen something like this. As the volume was high, the pressure was low, and when the volume was low, the pressure was high. And so we say pressure is inversely proportional to volume. Okay, this is a proportionality instead of an equation, right? If this was an equal sign, then I would actually need to know what the value of some k was that I was multiplying. So I could say P equals k over V, and I could find this k. I'm not too worried about it. For now, we're just saying the pressure is inversely proportional to volume. Then you did a similar lab, or a similar investigation, but this time you were measuring how pressure and the number of particles was related. Now to do this, it was a little bit different. So you were still holding pressure constant, not pressure, whoops. You were still holding temperature constant, and the other thing that you were holding constant was volume. Okay, so volume constant. And so what you did was we came up with this imaginary number of counting, and basically said 3 milliliters of air equals 1 puff. I think it was 3 milliliters. Anyways, yeah, about 3 milliliters of air is 1 puff. So what you can do is you can take your syringe and you fill it up, open to the environment, you fill it up to 3 milliliters, and then you seal this thing off on your gas pressure sensor, so there's no more air can get in or come out. And then you pull this out so that it's 10 milliliters, and you see that these 3 milliliters of air now expand to fill the 10 milliliters of air, and you would see the pressure goes down. Then you'd put in 2 puffs, so you'd have 6 milliliters of air. And when you do that, you would disconnect this thing, fill it to 6, then reconnect it, pull this to 10, see what happens. And hopefully what you saw when you did this one was that as the number of particles, and this has no units, it doesn't mean anything to say puffs, because a puff is whatever, how many particles of air, that as the number of the air particles increased, the pressure also increased, and this was a rather direct relationship. So now we can say pressure is directly proportional to the number of particles n. Again, it's not an equal sign. I don't have a k, I don't have a slope, but if there were no particles of air, it would be 0, so this does go through the 0, 0. It is a direct proportion. In the next experiment you did, you were actually looking to see how pressure was related to temperature, and so this means you were holding the volume and you were holding the number of particles constant. And so you just took your syringe and you actually this time it wasn't a syringe, it was a flask, and you put it in a variety of different temperature environments, and hopefully what you saw was that as you changed the temperature, the pressure changed in response to that. And we didn't actually measure 0, we were measuring temperature, but you probably had a few points up here and you noticed that as the temperature increased, the pressure increased. Now this one is a little bit interesting because at first it doesn't seem like a direct proportion. It does seem very linear, but if you're measuring your temperature in Celsius, then you're going to end up with a line that goes through like this. It doesn't go through the origin. It goes through some number here, and you have to extend it all the way back to here to a temperature you didn't measure at a pressure you didn't measure to get it to 0. Now if you do that extension, this should be around minus 273 degrees at 0 pascals. And remember, that's degrees Celsius. That's the absolute coldest temperature we can get. That's absolute zero. That's where all particles stop. And that is 0 Kelvin. And so as long as we measure temperature in Kelvin, then we should come up with the relationship that pressure is directly related to temperature as long as temperature is, or directly proportional to temperature, as long as temperature is measured in Kelvin, not degrees Celsius. If it's measured in degrees Celsius, then we have an issue, and we have to deal with that because we'd have a y-intercept. Okay. Now, what we want to do with these is put them all together. And if you think about it, we have three relationships. We had pressure is inversely related to volume, it's directly related to the number of particles, and it is inversely related to, directly related to temperature. Now, if you think about this like in terms of area, area is proportional to length, and area is also proportional to width. You can clearly see if I have a rectangle that's this big, then if I double the length, the area is also going to double, right? And so area is proportional to length, and it's also proportional to width. And when I combine these to actually get the formula for area, all I do is I say area is equal to length times width. Okay, so we're going to do the same thing here. I'm going to combine all these, and I can say pressure is equal, well, proportional to, we won't have an equality yet. We can say it's 1 over V times N times T. And then we're actually going to go ahead and multiply that V over to the other side, and we can say pressure times volume is proportional to the number of particles times temperature. Now, this is almost an equation. All we have to do is solve it for some pressure, volume, number of particles, and temperature, and multiply by K, right? So we say, and that's some constant. And actually the constant we use is R, and so we can replace that proportionality with an equal sign. We say pressure times volume is equal to the number of particles times this constant R times temperature. And the important thing to remember is this temperature is got to be in kelvins.